Okay, so I was requested to do just a little look at a video for sum and difference identities. I know these formulas can look a little bit on the overwhelming side when we first look at them. I'm not going to go through the whole proof side of that whole set of documents. I'm just going to kind of talk about how to use them and how we kind of execute that. So I have a couple of different problems that I prepared that we're going to go ahead and look at. So right away, let's just talk our way through these problems. So now right away, one of the things that I want you to notice is when you take the sign of alpha plus or minus beta, notice the plus or minus here leads to a plus or minus there. That means that if you're going to add two angles in the question, in the equation, you're also going to add. And if you minus something in the question, in the equation, we're also going to subtract. Now that changes distinctly in this one where the plus or minus switches places. So if you're deciding that you wanted to subtract two angles in the question, then that means you're going to actually add in the answer segment. And then the tangent is kind of bizarre because you'll notice that right here we have a plus or minus. And so when we add, but in the denominator, it switches signs. And then, so obviously that means a plus in the left side is going to lead to a plus and simultaneously a minus. So that can be a little confusing. We also have a couple of things about odd and even to play with, but these are the magic formulas that you need to know how to use. You do not have to have them memorized, although it's sometimes helpful just to recognize what we're looking for. So what I personally like to do is I take a look at a problem like this and I say, well, how can I break that thing up? And so what I would do is maybe break it up as a 3/12 plus a 10/12. Somebody else might have done a 4 and a 9. There's all sorts of different ways you could do that. As long as they reduce, they're going to reduce to values that are nice for us. Now, one thing I want to be really, really cautious about is the angle pi over 4 is an angle in the first quadrant. So no matter what I do, I will get positive answers. But 5 pi over 6 is an angle that's sitting in the second quadrant. And so because that's in the second quadrant, we kind of would know that anything that is in the second quadrant, only the sign would be positive. If it was a cosine or a tangent, that would lead to a negative answer. So I'm going to go ahead and pick this guy right here. That is the sine of alpha plus beta. So I'm going to go ahead and take the time to write that down. That was the sine of alpha cosine beta. I'm just using this formula right up across the top. Plus, notice a plus here leads to a plus there, cosine alpha sine beta. And all of my alphas, I'm going to be using pi over 4. So it's a sine of pi over 4 here, and it's a cosine of pi over 4 here. And my betas are going to be 5 pi over 6s. So again, in both situations, we've got that. So I don't know if it would help to do that, but notice here's alpha. And beta would be this guy right here. Beta is going to be my 5 pi over 6. So that's beta, that's beta, that's beta. And so that's kind of how I'm going to play the game. So from my unit circle, I know that the sine and the cosine of of pi over 4 is root 2 over 2. So that's a fairly simple idea. I also know that the cosine of any kind of pi over 6 is root 3 over 2. But since it's a cosine and it's in the second quadrant, I know that that value is going to be negative. And last, the sine of any kind of pi over 6 is a half. This goes with the promise that I made you in class that we will always have a root 6 in the top, we will always have a root 2 in the top, and we'll always have a 4 in the bottom. And so that's the end of my story. Now keep in mind, it's really easy to make a mistake when you have so much happening right here. So again, if I just make sure that I'm in radian mode, I'm going to go ahead and ask the question of my calculator to make sure that I didn't make a mistake. So I have the sine of 13 pi over 12. And if I try math enter to make it a fraction, it just won't do it because this is an irrational value. There's a square root sitting in it. So negative 2.588. Okay, so kind of a jacked up number. We're just going to leave it alone for the moment. I'm not going to use that. I'm just going to play with it a little bit. Now my numerator I claimed was negative root 6 plus root 2. and then I divided that by 4 according to this, and hopefully I'm going to get exactly the same answer. So that tells me I should have pretty strong confidence in the result that I have. All right, I'm going to stop share for just a moment and hit OK. So just making sure something was working appropriately so I didn't have to redo the video. So let's go back to that. Now, in this case, I chose to do a tangent, and this is kind of an interesting thing because some people will choose to answer this problem instead, because we could do that because of the fact that the tangent is an odd function. I could bring the negative out in front. This is really a matter of preference. Some people like one way, some people like another way. So I'm going to go ahead and go with this direction because I actually think that 2/12, which is pi over 6, plus 3/12, which is pi over 4, is a fairly simple set of numbers that are both in quadrant 1. So I really don't have to deal with the pluses or minuses that are actually going to take place. I just have to watch that I got this negative right here. So we're going to be using alpha as pi over 6 and beta as pi over 4. So I'm going to put a minus out in front because that's this minus right here. So it was supposed to be tangent alpha plus tangent beta all over 1 minus. Now again, that's a little strange, but it goes from this one. A plus leads to a plus on top and a minus on the bottom. Tangent alpha times tangent beta. And we don't actually write the times when we write those formulas out, but anytime you write things side by side in algebra classes, that means you're multiplying them. So that negative is a little bit of a booger. We got to be really, really careful. Referring back to our unit circle that we've done quite a few times, the tangent of pi over 6 is √3 over 3. Tangent of pi over 4 is 1. This is √3 over 3, and the tangent of pi over 4 again is 1. So this isn't so bad, but I don't really like the fraction in a fraction story. So I'm going to go ahead and multiply everything top and bottom by the number 3. And if I do, I'd get a √3 plus 3 on top, and I'd get a 3 minus √3 on the bottom. And I did tell you for the time being, it would be okay for us to leave our answer in that format, although if you were to keep going ever so slightly, there's a nicer resolution to this question that we could get to. So what I'm going to do is I'm going to use the conjugate. So if you look at the denominator that has a 3 minus √3, I'm going to multiply the top and bottom by 3 plus √3. Now that looks a little bit nasty, kind of gross, but just bear with me for a moment, and we're going to see what happens. I'm going to use the distributive property on the denominator, and notice that 3 times 3 is 9. Then I get a 3 roots of 3 and a negative roots of 3. Those are going to cancel. 3 roots of 3, negative 3 roots of 3. And then very last, negative √3 times negative 3 is negative 9. So this problem came out all the way down to just a plain old 6 in the denominator, which is a pretty nice denominator considering where we were. Now, as far as the numerator goes, if I distribute that out, I get a 9. I get 3 roots of 3 plus another 3 roots of 3 is 6. And then √3 plus √3 is well, just 3, I guess. So putting it all together, I have 12 plus 6 roots of 3. And you know what? This is kind of interesting that it's so nice because everybody here is divisible by 6. So I still have that minus in front from the original part of the problem, but I get a 2 here and a √3 here because everything cancels. So that's a fairly nice looking answer, but again, a lot of places I can make some mistakes. So let's take a look at the tangent of negative 5 pi over 12. Again, kind of a nasty looking answer. My final answer was negative parentheses 2 plus √3. That worked, but some of you may have stopped a little bit early, like right up here. Like you might have stopped with negative parentheses, and I got to be really careful here. I've got a √3 plus 3 divided by 3 minus √3. And that should also give me negative 3.73. So no matter how I structured that problem, it actually came out reasonably well. Okay, so moving a little bit deeper into the problem, this is the first one where I was going to use one of our reciprocals. So when someone asks me for a secant, the first thing I would do is I would just change it to a cosine. And in this case, I'm going to use the fact that it was an even function to just take that negative and throw it away. I'm not even going to worry about it. And so 7/12 being 4/12 plus 3/12. Keep in mind that this would be pi over 4, and this one would be, actually this would be pi over 3, and this would be pi over 4. Those are pretty nice looking answers right there. And so this is going to be my alpha and beta. So I had a cosine of alpha, cosine of beta. Now this is just going back to the formulas that we used at the beginning of the lesson. The cosine of alpha plus beta is cosine minus. Notice the plus leads to a minus, so we're going to need to be careful there. Minus the sine of that product. Now I promised you that we should get a root 2, a root 6, and a denominator of a 4. Now, of course, I hope you guys catch that I'm getting all of those values right off the unit circle. And so I have root 2 minus root 6 all over 4. But that was the answer to the wrong question. That was the answer to the cosine, and I wanted the secant. So the secant of the original problem was actually this value right here. Now, just like in the tangent, I did tell you you could stop here. It's okay. You're all right. This is a good answer. But if we wanted to go just a tiny bit further by using the conjugate, by multiplying by its conjugate, something really kind of nice happens. In the numerator, we have the root 2 plus root 6, and I'm not going to deal with it. But if I distribute out the denominator, I get 2 here. I have a root 12 and a negative root 12 that cancel, and then a minus 6. There's a 2, a root 12, and a root negative 12 that cancel, and then a root 36 or 6 that stay. So 2 take away 6 is negative 4. And you're going to notice that those cancel to leave a minus 1. And so we could finish off our story and just say that it's negative root 2 minus root 6, which is a pretty nice answer. So let's just see how we did on that one. So when I took the secant, now unfortunately I don't have a secant button, but I do have a 1 divided by the cosine button of negative 7 pi over 12. Now that's going to be probably an unpleasant looking answer. And when I did my original story, I stopped at 4 divided by root 2 minus root 6. And notice that I got a nice solid answer. But then when I kept going and I tried to do something a little bit more elaborate, I got negative root 2 minus root 6. And let's see if I actually did well on that one as well. And so notice that we got exactly the same result no matter what I did. Now, going a little bit further, what we can do is we can use this to prove certain things. Like if somebody says, hey, let's take the cosine and let's shift it to the right pi over 2. Well, what would happen if I took a cosine? Remember, take the cosine. Think about what that cosine wave looks like. It looks like a wave that looks about like this. And what would happen, in fact, I could keep it coming down right here a little bit. What would happen if I kicked that cosine wave to the right, pi over 2, and it would look about like this? Well, that kind of looks like something, doesn't it? Doesn't that kind of look like a sine wave? But I don't want to just kind of just think it looks like one. I want to know. So what I'm going to do is I'm going to pretend that this guy is alpha and that guy is beta, okay? So the cosine of alpha minus beta is cosine alpha, cosine beta, plus, remember there's a difference there, sine alpha, sine beta. And there's something really nice that happens because we know from basic trig that the cosine of pi over 2 is 0. And we also know from basic trig that the sine, I meant to write that as an x, sorry, that the sine of pi over 2 is 1. Well, that product just becomes sine X, which is not too bad. So let's see what that looks like when we take a look at it in the lens of Desmos. So here is the cosine of x minus pi over 2, and I said that when I reduce that down, I just got exactly the sign, and look what happens when I turn the sign on. Those are exactly the same waves, aren't they? So if I shift the cosine to the right, pi over 2, I do in fact perfectly get a sine wave, and I've proven that. Not a real shocking result, but a true one. And my last little problem, and this is actually something that I've put on tests in the past that has really kind of thrown people off their game a little bit, and they just didn't know what to do. So what we have right here is a problem where I told you that the sine was positive and the cosine is negative, which puts it in the second quadrant, remember? The whole ASTC thing. The sine is defined as opposite over hypotenuse, which is going to make 9 minus 4, 5. So this is going to be root 5. And I know a lot of people go, well, what's going to happen here? Well, this is really just thinking of this as alpha and this one as beta. So the sine of alpha, cosine beta, the formula says, again, going back, the sine of alpha plus beta was sine cosine plus cosine sine. And so if we put that all together, I get root 2 over 2 for the cosine with a sine. And over here, I have a cosine with another root 2 over 2 as well. And I kind of notice that I have a root 2 over 2 in front because they have that in common. And I have a sine plus cosine. Now, that's not exactly a pretty answer, but that's a reasonable answer that somehow if you take the sine and you shift it to the left, pi over 4, this is the wave that shows up. And I do understand that some of you might wonder why anybody would ever choose to do that. But the reason why you might choose to do that is in circuits, you guys have probably heard of alternating and direct current. So in direct current, the electrons only flow one way, but in alternating current, they shift back and forth, and they actually shift back and forth according to a trigonometric wave. And if you're hanging with me right here, what happens in alternating current, there's this little thing that's called a resistor, but it's specifically called an inductive resistor. And in an inductive resistor, what it does is it takes the wave, like the sine of theta that is coming through this thing, and it actually changes its phase. It actually just slows it down and lets it go, or speeds it up and lets it go, but it actually changes where it is on that thing. And so electronic engineers all the time have to know how that resistor is going to change the behavior of that wave so they know how to put that circuitry together, because anytime you have one of those resistors in there, this kind of thing is going to happen and it's going to change the behavior of that. But we have to have those resistors in there for a variety of reasons, because it helps us control the voltage and the current that are happening throughout a circuit. So that is kind of the end of my little presentation on sum and difference in trig. So I hope that helps, and I'll see you back.